Hi everyone, I'm Joyang Xiong from Rice University. This is a presentation for our work, Strong Lottery Ticket Hypothesis with Epsilon Perturbation. This is a joint work with Fangshuo Liao and Anastasios Kyrilidis. I would first like to introduce some background of our work. The lottery ticket hypothesis proposed by Frankel and Carbin back in 2019 says that a randomly initialized dense neural network contains a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. The subnetwork here is called the lottery ticket. So how to find the lottery ticket? Firstly, we train a randomly initialized neural network. Then we prune the weights with small magnitude. After that, we rewind the remaining weights to their initialization, and then we retrain them. Previous works had found that if instead of rewinding, we randomly initialize them again, the performance will be worse. This means that the initialization is important. The thing about the LTH is that it has been verified empirically, but it lacks some theoretical guarantees. So here comes the strong lottery ticket hypothesis, which says that we have a target neural network F and a randomly initialized neural network G, which is much larger. Then we can approximate F by pruning G. That is, we can let the best approximation error, eta, to be small, where eta is defined by the minimum of the supremum of the norm of the difference between the output of F and output of the pruned network, which is M composite G, where M is the mask. In this setting, there is no need for training, and it is easier to prove. However, the overparameterization will be much larger. So how much overparameterization does strong LTH need? In 2020, Pensier showed the following theorem. Let the desired approximation error eta hat be given, and assume F has L layers, and the width of little l's layers is dl for all L from 1 to big L. Then if G has 2L layers, and the width of the 2L minus 1's layers is dl prime, the width of the 2L's layer is dl, as long as dl prime equals O dl minus 1 log eta hat to the power of -1 dl dl minus 1 L, then with high probability, we have the best approximation error to be less than or equal to eta hat. So for short, if F has n parameters in total and L layers, then we need G to have O n log eta hat to the power of -1 n L parameters and 2 L layers. In our work, we would like to ask the following question. What if a small epsilon perturbation is allowed? In particular, by allowing a small epsilon perturbation, how much can we reduce the overparameterization requirement of G? The idea is to treat the weight change during training as some general perturbation around initialization. For example, consider the neural network G parameterized by W. Then we consider perturbation as adding a delta W onto W. Then we require the infinity norm of delta W to be less than or equal to epsilon. And we can study how varying epsilon affects the best approximation error eta, where here eta is defined to be the minimum of supremum of the norm of fx minus m composite g w plus delta w x, where m composite g w plus delta w is the pruned and perturbed network. Now let's back to the SLTH setting. So a key point of the SLTH proof is to consider the subset sum problem, which says that given n randomly generated candidate values xi, I from 1 to n, and a target value z, we would like to find the best mask delta from 0, 1 to the power of n to minimize the absolute value of the sum of xi delta I minus z. So the theoretical guarantee by Louikers in 1996 says that if xi are generated uniformly from -1 to 1, and eta equals O log eta hat to the power of -1, then with high probability, all z in -1/2 to 1/2 has an eta hat approximation. In our work, we consider a variant of the subset sum problem, which we call the epsilon perturbed subset sum problem. In this setting, we still have n random candidates, xi, and a target z. We have the freedom of choosing the mask delta. However, we also have the additional freedom of choosing the epsilon perturbation y, and our goal is to minimize the approximation error, which is defined to be the absolute value of the sum of delta I xi plus yi minus z. Our theoretical guarantee shows that if xi are generated uniformly from -1 to 1, and n equals O log eta hat to the power of -1 divided by 1 plus epsilon, then with high probability, all z from -1/2 to 1/2 has an eta hat approximation. We can then apply our results from the epsilon perturbed subset sum to the scheme of neural nets approximation. Here is an example of approximating a single neuron using a two-layer ReLU neural networks. Here, for the target network, the input is x and the output is just w times x. Initially, for the candidate network, the output is v transpose sigma ux. For the strong LTH scheme, we have the freedom of choosing the mask S on the vector U. Therefore, we consider the output of the prune network V transpose sigma S mask U X as an approximation of W times X. In our scheme of strong LTH with perturbation, besides having the freedom of choosing the mask S, we also have the freedom of choosing the epsilon perturbation Y on the vector V. Therefore, by choosing the epsilon perturbation Y and the mask S, we consider the output of the pruned and perturbed network V plus Y transpose sigma S mask U X as an approximation of W times X. As a result, our scheme of approximation requires less number of overparameterization of the candidate network. So here comes the theorem. Let the desired approximation error eta hat be given, and assume F has L layers, and the width of the little l's layer is dl for all little l from 1 to big L. Then if G has two L layers, and the width of the two L minus 1's layer is dl prime, the width of the two L's layer is dl, as long as dl prime equals O dl minus 1 log eta hat to the power of -1 dl dl minus 1 L divided by 1 plus epsilon, then with high probability, we have the best approximation error being less than or equal to eta hat. So for short, if we allow epsilon scale perturbation as compared to the strong LTH scheme without perturbation, we can reduce the overparameterization requirement of G by a factor of O1 divided by 1 plus epsilon. We also run some empirical verification of our theoretical results. Basically, we approximate a two-layer 500 hidden node neural network. For each weight W and for each eta epsilon pair, we generate candidates xi, I from 1 to n to approximate W. After that, we record the smallest n such that every weight W has an eta approximation with epsilon perturbation. So as we can see here, as epsilon increases and decreases. Also in this figure, when epsilon gets large but not too large, we need more increase in epsilon to make a decrease of n. So here comes another question. How to find a good epsilon perturbation? We hypothesize that gradient descent finds good epsilon perturbation. And in particular, we hypothesize that stochastic gradient descent finds good epsilon perturbation for pruning. To verify our hypothesis, we design an algorithm that runs 3 steps. The first step is to run a projected gradient descent under the constraint that the infinity norm of the delta W is less than or equal to epsilon. The second step is that for each pruning level, or say for each sparsity level, we run the algorithm edge pop-up to find the best pruning. And the third step is to just find the best sparsity accuracy pair. So here, the sparsity level means the percentage of weights that are being pruned. So a sparsity level of 0.1 means 10% of the weights being pruned. And here is our result. The red region is just the strong LTH scheme, where there is no perturbation. And the blue region is just the standard SGD training without any pruning. And we will go into the orange region later. So here, for each perturbation scale, among all sparsity level, we mark the highest accuracy, bold. So as we can see here, as the perturbation scale increases, the highest accuracy also increases. And this verifies our hypothesis that SGD finds good epsilon perturbation for pruning. There is also some other interesting finding. So for example, this orange region represents the place where SGD dominates pruning. So what we mean by this is that when the perturbation scale is large, the sparsity that finds the highest accuracy is actually 0. So this means that no pruning will let us find the highest accuracy. And especially here in the lower right dark orange region, this is the place where we apply the highest perturbation scale while also enforcing the highest pruning level. And this will cause us to get the lowest accuracy. So a possible explanation of this is that if we allow some large perturbation scale, the SGD will cause the weights to build some strong interdependence between them, so that any pruning will cause those interdependence to break and cause the accuracy to drop down. That's all for this presentation. Thank you for listening.